All right, so I'm going to walk through the third Explorer looking at the homework solutions so that you guys can check your answers versus the book answers. Some of these problems aren't the best problems, but it gives us a sense of kind of how this all goes together. And at the end, there's a problem that I don't expect you to work through, but it talks about how to estimate the lifetime of the sun. I'm going to work through a couple of calculations at the end of this video showing you one way that you could kind of get an estimate for that. So to begin with, we're talking about talk about the way that the solar system has been formed. So the solar system was from a nebula, so a gas and dust collection that collapsed and had this swirling disk. And then the most massive object would be the star that we call our sun. And all the other objects become in orbit around that plane, around the sun, and then they form that plane. And over billions of years, sweep out all the other kind of debris that's in the way, and we are left with our current solar system. All right. This is where it walks through, just like we did in our lesson video. If it was a fossil fuel combustion, then the sun would run out of fuel in about 1,800 years. That's obviously not the case. I'm not expecting you to solve this on your own, but we are going to walk through, again at the end, what this equation would look like and get an estimate for the amount of time that would take to use up the sun's fuel. When we look at the interior of the sun, we're looking at the layers of the sun. You can click on these icons and see what the different layers are. The question at the end here is talking about when does the temperature trend change? Well, that's in the photosphere. So the photosphere is up here.
Photosphere.
And if you
Thermal
look
radiation
at
is given off at the visible
just the different
surface, where the
temperatures,
sun's matter
you'll
becomes
see
transparent,
that you have this
6,000
shift in
degrees
temperature there,
Celsius.
kind of at the surface of the
Sunspots
sun.
appear here.
As we keep moving through it and we're looking at the sunspots, it gives you this graph, and you can see that you have these peaks where you have these large sunspot area. You have the overall percentage visible, so you get like a maximum of 0.5%. And you can see the time interval at the end, right? So 10-ish years is how long it's taking for these sunspots to grow and peak. And you see that you had a massive sunspot around 1960, because that's the largest part of your graph. So in looking at their answers, you see they last about 11 years. They appear in groups. And then again, 1960 was the peak that they covered, and about 0.5% were visible. And that's just reading the chart from above. And looking at the atmosphere of the sun, right, you see the photosphere is around 6,000 degrees Celsius, and then you have this jump in temperature in the chromosphere, and then the corona is actually going to be the hottest temperature. And so below the photosphere, the sun is dense enough to be opaque, right? You're not going to be able to see through it. And then the sun is going to emit thermal radiation in a continuous spectrum, and as it passes this chromosphere, then those other, the hydrogen and other absorb light, and they produce those lines in the spectrum that we see. And they also emit a radiation that's difficult to see when it's against a dark background, such as an eclipse. This is trying to match up these spectrographs. Really what you're again looking for is that the lines line up, right? So I have this line in the red spectrum here that lines up, right, in the kind of cyan and then the blue. So that would be how we'd identify this unknown element based on the absorption lines. You don't need to do the hands-on lab. We've talked again in the lesson about this red shift and blue shift. So blue shift is when it's approaching Earth. Red shift is when it's moving away from Earth. And that's just the shift in the visible light spectrum. And if there's no relative motion, we just expect that constant light. All right, this is asking which of those would show motion away. So motion away is going to be a red shift. And we can see that this one, the bottom one, has that shift to the red. Right, we have that red shift there. I don't love these problems. They're not a great problem. We just, again, have to understand for us this red shift and blue shift as approaching and receding. Same thing with this one. It's not a great problem. But if you assume that the sun right? That the Earth is somewhere in here, and we're all rotating in this direction. So if this is the Earth, and we're not moving away from it, then there's no shift. The blue shift would be the approaching towards the Earth, and then the red shift would be moving away. And that's the only way that I can really interpret their diagram to make sense. All right, so that's it for this piece. I'm going to put another video on the end of this one where we look at, again, this calculation for the hydrogen fusion timeline on the sun. We'll look at this diagram and talk about how that gets created. All right, so we're going to try to talk about this, how the sun, the reaction from the sun, using hydrogen to fuse into helium as a fuel source, is how long that's going to last. And we're going to compare that to the 1800-year estimate for the combustible fuels. So the book is going to give you this image showing this fusion reaction where you have these hydrogen atoms that are then going to be fused into helium. And when we look at it, what we see is we have these kind of 6 positive values over here. We get this helium atom, and then we have, again, these hydrogen atoms, and then we have these 2 positrons that are emitted as well, plus obviously a lot of energy. We're looking for the energy component. So we're going to try to write an equation for this. I see that I have these 2 and these 2 on both sides, so I'm going to ignore those for right now. And what I'm going to write is that I get 4 of these hydrogen ions that are going to be on one side, and then on the other side I'm going to have a helium atom, and then the 2 positrons that exist. And that's the setup, that's the start. We're going to, from there, just use the masses that are given us to try to figure out a mass balance. So if I was to figure out the mass that was given for those hydrogen ions, it would be 4 as 1.6726 times 10 to the negative 27th kilograms is going to be equal, not entirely equal, to the helium, right? So that's 6.6442 times 10 to the negative 27th kilograms plus 2 times the positrons. So that's 2 times 0.0009 times 10 negative 27th kilograms. And this is an exponent. All right. Really what I'm interested is in the change in mass, so that mass imbalance. And when I get that, it's small, negative 4.44 times 10 to the negative 29th kilograms. So it's a small mass difference. What we're really interested in, though, is using that mass difference using the energy. So E equals mc squared to calculate the energy difference. So to do that, we know that for each of these reactions, I'm going to have that mass imbalance. So I need to figure out basically how much hydrogen do I have in the sun. It gives us an estimate. It says that if the mass of the sun has the ratio of 3 to 1 of hydrogen to helium, so hydrogen to helium, what that means is in this ratio, if it's 3 parts, if we have 4 parts and 3 of them are hydrogen, then we have 75% of hydrogen that we have available for this reaction. So if I wanted to figure that out, I would say that my mass of hydrogen, how many of those are in there in terms of kilograms, is 0.75, that's 75%, times 2 times 10 to the 30th kilograms. That's given as the mass of the sun. And what I want to know is that is going to give me how there's the bulk mass in kilograms of hydrogen to figure out how many actual of atoms I have. I want to divide that number, this number here, by the mass per hydrogen, right? So let's just make it a simple number. If this was 10 kilograms and each of these was 1 kilogram, I would have 10 of these hydrogen ions that I could use. But it's not an easy number, right? It's a small mass, so I'm going to divide by the 1.6, the same number that was from up here, 1.6726 times 10 to the negative 27th. That's how many hydrogen per kilogram. And then I want to divide by 4 because I have 4 of them that are going to need to be producing this energy. All right. When I do that, basically that gives me the number of reactions that the sun can emit. And the number of reactions is going to be here is 4.44 times 10 to the negative 29th kilograms. That's the difference in mass. And then I'm going to take that. Sorry, I wrote down the wrong number. This is the number of reactions is a large number. It's 2.24 times 10 to the 56. So that's how many of these reactions I can create. Each of them is going to produce some certain amount of energy. So E equals mc squared. And the mass that we're using is this mass difference. So it is going to be the 4.44 times 10 to the negative 29th kilograms, very small, times the speed of light, 3 times 10 to the 8th squared. And when we do this, we're going to get a number of joules. And so the number of joules that we get is this. So I'm going to get 8.9. So I'm going to get a small number there, but when I multiply it by the number of reactions, I'm going to get a large number. So I'm going to get 8.9 times 10 to the 44th joules, which is massive. And if I change that to kilojoules, I get 8.9 times 10 to the 41st kilojoules. So that's how much energy the sun has to emit. What we need to know is basically the lifetime, right? Like how long is it going to take to do that? So what we need to do now is use the rate of emission from the sun. So when we use the rate of emission from the sun, we're going to basically, to figure out the lifetime, right? We use the amount it has, the kilojoules we just figured out, and then the kilojoules per second that is given in the book. And when we divide those numbers, so we take the rate of emission and then the energy that we just found, what we get is 2.4 times 10 to the 18th seconds. And then when we convert that to years, so taking seconds, turning it into minutes, turning it into hours, days, and years, we get on the order of 7.5 times 10 to the 10th, which is now billions of years, which is actually probably too big, right? We don't get, this would be like 70 billion, which is too big. We're on more the order of magnitude of 5 billion. You can see we made some simplifications here. The take-home point is that the billions, right, is more accurate for how long this fusion takes because it's a much more efficient reaction than the 1800 years that you would get from just the internal combustion engine. I'm sorry, not engine, but internal combustion of the fossil fuel combustion. All right, so again, not expecting you to obviously work through this, but understanding that Why suns and stars last so long is a couple of things. The massive amount of elements that they have to fuse, and that fusion is such a highly productive form of energy production. All right.